All right, welcome back to week 12. Here's another example problem. I've just buried you in example problems. This is out of Miriam and Craig, and it is a rigid body analysis problem. It's not terribly difficult. Setting the thing up is really what I want to see more than anything else, but let's get into it. The part that is problem is this one right here. In addition, that's a time-consuming and annoying thing to do, to use the initial conditions in something like this. So I would not ask a problem on an exam like that because it's just too much of a headache. So anyway, let's describe the problem. We have a cylinder that's 50 kilograms and it has a radius of 0.5 meters and a spring constant right here of 75 newtons per meter and a damping coefficient of 10 newton seconds per meter. We want to find the undamped natural frequency, the damping ratio, the damped natural frequency, and the period of the damped system. All right, so this is not stuff that's kind of recent for us, but we still need to be able to do it. So I'll start out with my FBD and IBD. Draw two circles right here. There's a little fun. There's a trick to this that we're going to see in a second. All right, so we got our weight onto the thing. Don't really need that. Well, of course, we're going to have a normal force coming back up right here. And then we're going to have a friction force. Now we have to decide which way it's going to rotate. And the book kind of did that for us. We're going to say that it's in the midst of rotating this direction. Right? So, and therefore it's going to be accelerating. And we're also going to assume it's accelerating in that direction. And it's hard to do this without like having some physical thing onto there. But if something is rotating right here, and we put a gap in between here, and it's rotating this way right there, and now you think about what force does the ground see as this thing is gripping? Let's even let it slip a little bit right there, right? It's the ground is seeing a force that's going in that direction. If that's the case, then this guy must be seeing a force that's coming in this direction. If you missed that, play it back. Think about this thing moving and what it does to the ground. And let it slip a little bit, and you'll see that it is putting a force onto the ground. Well, if that happens, that means the ground is putting a opposite force onto the wheel. So that's why the friction is going in that direction. Once again, if you can't understand what I mean, go back. Maybe pick up something round and kind of like just turn it before it touches a gap on the ground, and then see that it is skidding onto the ground and which direction is causing a force. Okay, so these are loads that are between the ground and this, and now we have to the loads of the spring. That force of the spring is going in that direction, and the force of the damper is coming in that direction. We'll get back to those in a second. We also have this piece is accelerating, mass times acceleration in that direction, and it's also rotating. I call it alpha, but we go theta double dot most of the time. But it's moving in both of those things. Now, the book's solution to this is to do two equations. I say you could do it in a single equation because you can go this, take the moment about a point, and let's give the point a name. I said that was point A. So point A, and we can take the effective moments about A. Something we might need to know, good to know, we need I. Oops, don't do that, come back there. Let's find I is a disk. About its center is 1/2 mr squared. We can go ahead and put in values for some of these, I think is fine. So 50, and the radius of the thing is 0.5 squared. And did I put a number in there? No, I didn't do it. I guess I waited to the end. What is wrong with me? I don't know. Why can't I just go on standard script? Interesting. Well, I guess I didn't do this, so forget it. Let's just stick with what's on the page. I don't have to improvise. I'm tired. So the reason why I chose that spot A is it eliminates the friction, it eliminates the normal force, it eliminates the weight. So the only thing we have going on for us is a moment that's going to be. Oh, and by the way, I should have written this somewhere that the Fs is equal to k times x, and that the Fd is equal to c times x dot. Oh, ooh, do we want to turn it into theta? I decided to do everything in theta, which is different from what the book did, okay? So don't be mad at me for doing something different. I decided that we're going to go c times r times theta dot, and this is going to be k times r times theta. So when we go up to here to write it into there, go up into here to write it up into there, we got ourselves a k times r theta is a force, but we need it to be a moment, so it's squared plus a c, because this is r right here. Okay, make that clear. That fs times r, but fs is kr theta, so the moment is kr squared theta. And then we also have the same thing happens to this. Once again, from here, it's going counterclockwise, so it's positive. Now this equals, and as I mentioned, we had 1/2 mr squared theta double dot is for the rotation of this, but we're doing it in effective moment. And by the way, it needs to be negative because it's going clockwise. Otherwise, all of our signs will be wrong. Let's see if I can squeeze in the negative sign. There you go. And then, but also we have, that's why I'm doing the effective one. We need this mass times the acceleration times r. But that acceleration, when we're right here at that spot, we know in a no-slip condition, not slipping, that the acceleration is going to be equal to r times theta double dot. So I said it's going to be mr theta double dot, but remember that is just the translational. We need to have it up into a moment, right? So it is an inertial force. When you go mass times this acceleration, we need an inertial moment, so we need to put those into there. We could also, by the way, do the parallel axis theorem and just change what the moment is and make it the moment, a mass moment of inertia about that. So we rewrite all of these things into the equation of motion, which is usually going to be the main thing that we're going to try to concentrate on. But let's see, it's going to be end up being 3/2 times mass times r squared, right? Because you have 1/2 plus 1, so 3/2, and then have theta double dot, and then plus cr squared theta dot plus kr squared times theta equals 0. It is not a forced problem, so this is a homogeneous equation. Nice. And we could do one more step in our pursuit of the equation of motion. We divide through and get 2/3 c over m. Interesting, the r goes away, right? Plus 2/3 k over m. So that right there is a major milestone in this problem. We have the equation of motion. When I ask for an equation of motion, I would prefer that you keep the work through onto this. Now we can actually put numbers, values onto all of these things. We could have done that earlier. I don't know why we didn't, but we know that this right there is omega n squared. So omega n is the square root of 2/3 k over m, or 2/3 k 75 divided by m, which is 50. So omega n ends up being, interestingly enough, 1. Which matches what the book says it was going to be. You can find, all right, so this guy right here, we could know from our form, is equal to 2 squiggle natural frequency. So we have the natural frequency, so we can find it. And with it, we can find, so we said that 2, let me get another color so I can differentiate. I might actually really go to the next page. I'm working a little harder than I need to. So we said that 2 squiggle, come on. Omega n is going to be equal to 2/3 c over m. So I wrote that what we have is squiggle equals 1/3 c over m natural frequency. 1/3, our c is 10, our m is 50, and our natural frequency is 1. So our damping ratio, which is one of the questions, is 0.06667, which was one of our questions. Now we need the damped natural frequency, but we have all the ingredients for it already. Remember, that's omega n times the square root of 1 minus squiggle squared. We had 1, and square root of 1 minus, and we just found this, of 0.06667 squared. And we get 0.9978 radians per second. And bingo, we got the same thing. And now we need to know the period. That's just simply taking the 2 pi and dividing it by the damped natural frequency. So that ends up being 6.297 seconds. And if we go back up there, 6.3, yeah. This next part right here, in addition, determine x as a function of time and the cylinder is released from rest with these initial conditions. It becomes a little bit of a pain because we, for one thing, we did things in theta. So our solution to this would include those terms. And they also, in that book, were in a standard form, usually using the same procedure, and we didn't use that procedure. We didn't use a magnitude and a phase all the time. So adapting their solution to the approach that I took was just more confusing than it was worth. So I'm just going to leave it at this. This was a suitably long problem, I think, for an exam.